Hi everyone, I'm Zhechen. Nice to meet all of you through the wonders of the internet. And today, I'm presenting a novel algorithm designed by Emin and I to identify cell sector clusters using massive mobile usage records. This work is completed while both of us were at DataSpark and is a proposed feature for the optimization product for telco operators. In the traditional cell planning process, network planners use cell site as the base unit of planning. For illustration, here is a cell site and the coverage of its sectors. The black dot with the antenna sign here represents the location of a cell site. In 3G and 4G, directional antennas or cells are commonly used and arranged in 3 sectors to provide cellular coverage. The sectors are represented by the shaded hexagons. Here are 2 more sites and their sectorized coverage. And now, let's overlay the layout of the town onto these deployments. Let's say the downtown area here have high demand and is causing congestion on some cells. Network planners use congestion as a key indicator to plan upgrades, and they aggregate congestion at site level. This way, they're likely to conclude that 2 of the 3 sites need an upgrade. Based on the layout of the town, it's not hard to see that this will result in over-upgrades, that is, surplus bandwidth on sectors with low demand. And these over-upgrades ultimately results in a lower return on investment. If we instead view the user demand from sector level, we can see that only some sectors are covering the downtown area. Better still, these sectors may be able to share user demand such that only upgrading some of the sectors would help to ease congestion. This saves costs as compared to doing blanket upgrades and thus improve ROI. We call a group of sectors a cluster, and cell planning using cluster and sectors as base units instead of sites can optimize a telco operator's ROI. But how do we identify those clusters? Perhaps geographic simulation can help. To run the simulation, you need to provide various properties of a cell, including the azimuths, which may or may not be accurate. If there are hills and mountains, then you have to do ray tracing. These operations are complex and heavily rely on accurate data. Thus, geosimulation systems are expensive to implement and expensive to operate. But wait, we have a simpler and cheaper solution. By harnessing the power of big data, we designed the data-centric SCUT algorithm to automatically discover cell sector clusters. SCUT stands for Sector Clustering with User Transactions. So naturally, SCUT uses mobile usage records, which is an hourly aggregation of various XDR data sources. These are basically transactional records maintained by a telco operator and are usually kept for billing purposes. This data is readily available. From there, we need to know all cells that each user connected to in every hour and the properties of those cells. We need the user ID, which can be either MSI SDN or MC. We also need the date and hour of each transaction and the cells that this user connected to within the hour. We then need an operator cell inventory to look up its various properties. We use the CGI column here as a key. We then need to know the frequency band that this cell operates on, its geographical locations, and as well as the type of location that this cell is deployed in. So how does SCUT transform the data sources into insights, that is, the cluster definitions? First, it builds an undirected weighted graph describing the utilization of multiple cells by each and every device on the network within every hour. We call this graph the shared usage graph. This graph was built at cell level and then aggregated to sector level. So after aggregation, each vertex in the graph is a sector. We use the edge weight to denote the frequency that this pair of sectors gets used, and then we normalize the edge weight. An illustration of the graph is shown here. The thickness of each line illustrates the normalized edge weight, which is bounded between 0 and 1. And then, it enumerates the disjoint graph cliques from the shared usage graph. We use 2 scores to rank those cliques, coherence percentile and total user hours. This ranking is used to select the disjoint cliques and output them as cluster definitions. And as an illustrative example, the SCUT algorithm would output the following clusters from the shared usage graph on the left. To link 2 cells in the shared usage graph, they should be able to share the demand from a particular device. Thus, the device should be able to connect to both cells while being stationary. Since a user could easily travel a fairly long distance within an hour, the stationary assumption may or may not be met by every user hour in the mobile usage records. Thus, we have to devise filters to remove those moving user hours. Figure 4 and 5 are some of the data exploratory results we've done on the topic. Figure 5 on the left is a histogram of the number of connected cells per user hour. Note that its y-axis is in logarithmic scale. Figure 4 on the right shows the location of every cell for 2 outlying sample user hours. On subfigure A, a user has connected to 143 cells within an hour, which is on the extreme end. In subfigure B, the user connected to 30 cells within an hour. So we draw the location of those cells onto a map, but the underlying map is not shown for anonymity reason. Referring to the scale of the drawing, it's obvious that these users are moving within the hour. The first guy was probably driving along the freeway while having an important business meeting on the phone. So, since 99.9% of user hours do not use more than 30 cells, and as I mentioned, outlying user hours are likely on the move, we should just filter out these user hours. First, we set 30 as the cutoff value for this particular dataset that we obtained, since it kept the vast majority of user hours. And second, we use the estimated maximum coverage range, detailed in Table 1 on the next slide, to filter out user hours within which connected cells do not have an overlap in terms of coverage. The overlay of Figure 4 gives an illustrative example. Suppose the orange circles are the estimated maximum range of 2 cells on their respective centers. And clearly, these 2 circles do not overlap. Because we don't have azimuth information, we have to assume that this cell can be pointing in any direction, hence the circle. So a user hour will be removed if any one pair of cells do not have coverage overlap. This is the table of the coverage range estimates per band. The effective range is determined by 2 properties of a cell: location type, that is urban or rural deployment, as well as its frequency band. So these estimates are obtained from our partner operators network engineering team. At the second stage, SCUT exposes 3 cutoff parameters for output tuning. The minimum normalized edge weight is used to specify the shared usage graph before running clique detection on the graph. In this example, the for clique will no longer exist if edges connecting one of the vertices pairs are removed. The minimum coherence percentile and the minimum total user hours are used to filter the cliques. Clique coherence is calculated as the sum of normalized edge weights across all edges within the clique, divided by the size of the clique. This value is bounded between 0 and 1, and intuitively, it calculates the relative denseness of a clique with regard to its neighboring cliques. The total user hour is simply calculated as the sum of all original edge weights, that is before normalization, within the clique. To run experiments on the SCUT algorithm, we obtained real data from our partner telco. We obtained a full month or 30 days of mobile usage records, which contains about 13 billion rows. We also obtained the cell inventory of a partner telco, which contains about 200,000 cells. To benchmark the performance of a SCUT algorithm, we obtained the cell performance dataset of the same month. This data is exported from the operator's operation support system, and here's the schema. This dataset basically records the hourly transmitted data volume on each cell throughout the month. We ran experiments to see whether the SCUT clusters are more consistent in size when viewing user demand, and the conclusion is definitely affirmative, according to this chart here. Let me explain how we obtained the numbers in the chart. First, we made the following assumptions. 1. Cells have similar user demand pattern if they serve a similar group of users. And 2. We can use the time series of hourly data volume of a cell to approximate its user demand pattern. That's where the cell performance data comes in. We use the time series of hourly data volume per day per cell to represent the demand pattern of a cell for the day. And we do this comparison day by day across the whole month. We treat each time series as a 24-dimensional vector A. And here's the second vector B to compare with. Since everyone spends more time on their phone during the day and less at night, every cell's pattern kind of looks alike. So to remove this high similarity, we calculate the residual vector. We cover more on this in the paper, but I will skip it here due to time constraint. The residual vectors are then used to calculate cosine similarity. To obtain the 3 data points on the chart, we calculate the similarity between each cell's pattern and that of its assigned sector, site, or cluster, and found the best set of parameters that makes the SCUT cluster stand out. The pattern of sector, site, or cluster is basically the sum of all cell patterns within. Looking at the chart on the right, it's clear that SCUT clusters outperforms the operator-defined cell sites if we set a good set of parameters. Also, sectors have the best residual similarity. And this actually kind of confirms our assumption 1, because cells within a sector all faces the same direction, so they are naturally expected to serve a very similar group of users. Using the best set of parameters that we obtained previously, we generated the SCUT clusters using real data. The value of each parameter is listed on the screen. Here are some examples drawn onto a map, but again, the underlying map is not shown. The urban area has denser cell deployments, but most of the discovered sector clusters are on the same site. In contrast, rural area has more sparse cell deployments and has sector clusters across multiple sites. We believe this is because the best set of parameters that we obtain is more optimized for detecting clusters in rural area, and that a separate set of parameters is needed to better identify clusters in the urban area. Here is an interesting example. This is a 2-sector cluster that I found while checking the results. And to rationalize the cluster, I enlisted help from satellite images. These 2 sectors are shown as black dots on the illustrative satellite image. The image shows that the neighboring land area appears to be a rather small town without many houses inland. And however, there are a number of fishing harbors here with various boats and ships on the sea. And thus, we can reasonably conclude that these 2 sectors are covering the sailors and fishermen on the boat, and that's why it formed a cluster. If there's congestion in this area, upgrading one of the sectors is likely to satisfy the demand. From the previous example, and actually throughout the whole presentation, we can conclude that SCUT clusters offer useful insights to network planners. Comparing to geosimulations, SCUT uses only easy-to-access data sources and operates at a lower cost. The clusters could then help telco operators to plan upgrades with optimal ROI. In all, we have proven the value of the SCUT algorithm. That's all for my presentation. Thank you for listening, and now it's time for Q&A.